Thanks for having me, and thanks everyone for coming to my talk. I'm Justin. I lead the page algorithms team at Netflix. So we're responsible for figuring out what recommendations to put on your homepage. So if you like your recommendations, you can thank my team, and if you don't like them, then you can probably blame me. So as someone who works in recommendations, I get often asked, hey, tell me something, what should I watch? Give me some recommendations. And really, unless you're kind of into time travel movies like me, you're probably not going to like what I'm going to tell you. But I'm guessing that everyone here today is, for a machine learning conference, I'm interested in learning some recommendations about how we go about building machine learning systems, which is something that I think I can hopefully provide some decent recommendations about, given how much machine learning we do at Netflix. So to get started, when I talk about Netflix and machine learning, of course, the first thing that people typically ask about is the Netflix Prize, which was the competition we launched back in 2006 to do rating prediction. And that was back in the day when Netflix was mostly known for sending red envelopes to the mail. But when we fast forward to 2015, we're now an international instant streaming service, and we started producing our own content. So our world has changed dramatically, and our approach to recommendations has changed as well. Just to give you an idea of what scale we're operating at now, we have almost 70 million members. We're in about 50 countries. We have over 1,000 different types of devices. We stream over 3 billion hours a month. And we use about a third of the peak US downstream internet traffic. So we make sure that everyone can make the most of their internet broadband subscription. So in this new world, what is the goal of our recommendations? Our goal is to help our members find content that they're going to watch and content that they're going to enjoy watching so that they're happy. And then because we're a subscription service, we'll be happy because they'll stay with us and pay us more. So the way we do this now is by making everything into a recommendation. So when you log into your Netflix page, you see rows like dark comedies featuring a strong female lead, or because you watched House of Cards, and how we select those is personalized, and as well as the ranking of all the videos in each of those rows are personalized in sets of recommendations. So over 80% of what people watch on Netflix comes from these recommendations, and those recommendations are driven by machine learning. And we have lots of different recommendation systems that we've had to set up and use machine learning for. So I'm going to talk about how we go about building some of the software to do that. But before I do that, I just want to talk about, when we talk about machine learning, we think about, the problem of applying machine learning as involving kind of 5 different steps, and ideally we improve upon any of these to make our algorithms better. So one is defining the right problem. So, what are you trying to do? Are you, what kind of rank? Where are you trying to apply ranking? Is there some new feature of the site you're trying to improve? Then once you figure out what that is, deciding what labels and what data and what features you're going to use in your algorithm, picking a model and an algorithm that you're going to want to train it, as well as a metric that you're going to try to optimize. And then we go through this process of improving upon any of these different aspects in order to improve upon the algorithms. And kind of like Xavier showed, we have a whole zoo of algorithms that we apply to these problems. There isn't any one silver bullet that we found. So we apply pretty much everything in the book, from basic regression to a lot of matrix factorizations. We use restricted Boltzmann machines, deep neural networks, Markov models and graph algorithms, clustering, LDA, decision tree models, Gaussian processes, et cetera. And the reason we use all these things is that they each have a unique purpose that we find, and that's the reason that probably most people in the audience have heard of at least most of these. So when we're trying to build software for doing machine learning and recommendations, what are the aspects we want of our system? So we want our recommendations to be personal. They need to be accurate, so we're showing you things that you're actually interested in, not things you're not interested in. They should be diverse because everyone has a diverse set of interests. They're not typically just interested in one thing in their life. They need to be novel so that we're not just showing you things that we already know that we have, and to help you find actually things that are new. And they should be, importantly, fresh, which is that they should be changing and responding over time as people provide more input. On the software side, of course, we need things that's going to be scalable for the whole size of our user base. It needs to be responsive so that when people interact with the system, it'll change and adapt based on that. It needs to be resilient, so we run in the cloud, so typically things can happen, and we want the whole experience to stay up as much as possible. And it needs to be efficient because we're a business, and so we can't spend an infinite amount of resources on running our system. And finally, it needs to be flexible because machine learning is a very iterative process to develop, and we need to be constantly experimenting with new ideas. And so we're always trying to find that happy space between the two where we have the best of these two sets of objectives. Luckily, we have a great software stack that we're able to build on at Netflix, and a lot of this is either open source technology or ones that are technology that we've built in open source. So you can read a lot about these things on the Netflix tech blog, but generally, we use a Java-based stack in Amazon Web Services. And so if you're interested in some of these things, you can read about them or look at the Netflix GitHub page. So that kind of gives you an overview of how we approach machine learning and software at Netflix. So now I'm going to talk about particularly some recommendations based on the lessons we've learned for building machine learning software. So the first one is to be very flexible about where and when computation happens in your system. So this is a blueprint for a typical system architecture for one of our recommendation algorithms. And I'm not going to go too much into the detail of this diagram. If you want to read about it, again, we have a blog post that kind of talks through it. But at a high level, we try to break up the problem and think about letting our algorithms run both in the offline world, where we process big batch data, typically run our batch learning algorithms, the nearline world, where we have events coming in an asynchronous manner, and we can do things like apply online learning or model evaluation, and then the online world, where we have to respond very quickly to real-time requests and actually serve the responses. So if we take a problem like a matrix factorization algorithm, how do we go about placing these the different parts of the algorithm across these three parts of our system? So in the offline world, for a simple matrix factorization, we might start off by sampling a user by item matrix X, where we might put in the plays as ones in this big sparse matrix. We'd run some typical learning algorithm like SGD to then decompose that big matrix X into a small and thin matrix of user factors and then another matrix of item factors. And once we run this procedure, what we do is we actually throw away the user factors and then only publish the item factors. And then, of course, we need the item factors to actually perform recommendations, but in order to do that, what we do is we publish them and then use the most fresh data we have in our system about what people have watched in order to resolve for the new user factor each time based on each update of someone watching something. And then that lets us to then rescore and produce the most fresh set of recommendations based on their input, which we store in a cache. And then once the next request for a homepage comes in, we can apply some online contextual filtering by looking at the pre-computed scores and then serve up the final set of recommendations. So switching gears now to thinking about, okay, so we talked about how we split things up across the system. How do we think about doing distribution of our training algorithms? And I think similar to what Chave talked about, we tend to think about starting with the easiest layers first. So the first thing is thinking about, well, we run a lot of different regions, or we have a lot of different subpopulations that we're interested in modeling. So that's the easiest thing to parallelize, because each of these models really are independent, and we can distribute those pretty easily. The second stage that's easy to parallelize is that of hyperparameter tuning, because here you just need to select a set of hyperparameters and then send it off, and then either do something like a grid search where you actually don't really need to do much coordination, or do something better like Bayesian optimization techniques where you just need to send back your value of your metric and then use those to pick the next set of parameters to optimize. And finally, we break it up so that once you finally get down to each subset of your training data, which is where people typically focus on for distributed machine learning algorithms, here we can either do a distributed algorithm or use multi-core parallelism, like an algorithm like Hogwild, or use GPUs for things like deep learning. And for an example, that's typically how we typically break this up for something like training neural networks. What we would do is first, because we run in an international setup, we would break up the data and have different algorithms running in different AWS regions. For machines in the same AWS region, we'd use a cluster scheduler and then a hyperparameter optimizer like Mo or Spearmint or the newer one SIGOP for doing that optimization, and then something like Mesos to do coordination. And then within once we've set each set of hyperparameters, we would let that run on a single machine using highly optimized CUDA code on the GPUs. Third recommendation, design not just design your application software for experimentation, not just your lab software where you're building things, where you're just trying out your ideas. So to motivate this, I want to give an example of the typical development process I've seen people go through when building machine learning systems. So it starts out, you have a great idea for how to apply machine learning to a new problem or to improve an existing algorithm. You then go off and you find some relevant data that you're going to use and to train your model. You spend a lot of time doing some offline modeling in your favorite language, be it R, Python, MATLAB, etc. And you spend a lot of time iterating and finding that perfect model that does well on your data. And then you finally say, okay, I got it. This is going to be great. Now we just need to put this in production and figure out if this is going to work or not. So then you go and say, okay, now I need to implement this in the production system. And that's where the problems start happening. You start realizing, oh, there's difference between what the production system sees in the data and what I was seeing in the data. So okay, we'll figure out how to kind of realign things. Or you figure out, oh, when I put this in the application, it's already doing some post-processing on top of the output of my model. And I didn't account for that when I was running my system in my metrics. So I need to go back and tweak that, and that changes the model I build. Then you might run into some performance issues where you have to change how your model is configured, or you find discrepancies in the code between the two. You spend a lot of time iterating on that. It's not until you finally put all that together you actually see what is the actual output of your final system look like using this new model you've built. And then maybe it doesn't look at all like what you're expecting, and so you have to go back and figure out, well, was the problem my original idea, was it the data, or was it the offline modeling? And this can take a lot of time and involve different people. And it is not an ideal thing to constantly be dealing with all these problems that can go wrong. And really the problem typically I find boils down to that of just having two implementations of the same thing. So it starts off, you have your idea, you have your experiment code, you build something, you put it into some production code, but then there's this wall between them, and then those things can easily diverge because they're not kept in sync. So what we try to do is instead build one shared engine that both the experiment code and the production code can build off of, so that we can easily move things from experiment to production, and then that makes it easy to do experiments in production when we're doing A/B tests, as well as offline experiments using the production components, so we're able to simulate exactly what would come out of the final system. And so because machine learning is iterative, we try to lean towards production as much as possible and make it so that we can make the application itself easy to experiment, not just the lab environment that we're building things in. The fourth recommendation I have is that it's great to make your algorithms extensible and modular. And the problem here I see is that a lot of times, when things get going, people take a kind of black box off-the-shelf machine learning algorithm, they put in some data, they try it out, and it doesn't work, and it's not clear why it doesn't work. And oftentimes, these just kind of off-the-shelf algorithms implementations aren't very tuned to the exact problem you have or to the data set that you have. And so rather than kind of having like something be all or nothing of saying, oh, random forest doesn't work, or neural networks don't work for this problem, it's much better to have a kind of an open box where you can kind of see how all the different parts of the system are working, and so that you can tailor them to the different implementation, or the different specifics of your problem domain. And this can be something along, this is, the first level simplicity here is, or first thing to do, which I think some of the more modern packages have been better about, is actually making sure that you do have different separation of your algorithm and your model, so that you can plug and play different types of algorithms and models and swap them out. But then also support composing algorithms together, because oftentimes it is an ensemble of multiple things that's going to do better. And the way that we typically think about trying to provide this modularity is by starting kind of at the most basic level and then making building blocks all the way up, using the concepts that people are familiar with. So starting with the basic things around linear algebra or statistics, then thinking about how you have representations for things like models, features, and ensembles, or loss functions, distance functions, kernels, methods for doing optimization, inference, layers, activation functions, etc. And then by expressing what you want to build in terms of these familiar concepts, you really make it the job of the software that's gonna run the system to actually put these things together and find the most efficient way to run them. And so this is an example of what I mean by making things kind of more tailored, and it might be a little hard to see, but this is an example from some open source software that I worked on before I joined Netflix, which is the Cognitive Foundry. And the idea here is that if I want to take something like random forest, but then put in some custom splitting criteria, based on some new idea I have or how to adapt it to the system. I might just want to be able to drop that into the tree learning algorithm so that I can easily change then how that's going to be used in a random forest. And then I do machine learning, but I find that sometimes I'm very impatient for waiting things. So I say I want to just only let this run for an hour, so I can easily add in a custom stopping criteria to do that. And then finally, in each iteration, I may not have like an off-the-shelf error metric I want to use. I might have something very specific for my domain, so I can easily plug that in, and so it's called each time. And then finally, I can just run this whole thing, and I'll get kind of something that'll run and report the metric I want and stop in the time I wanted, and then look at the result. And by having just these kind of basic points of being able to plug in and tailor things, you're able to get, I think, a lot more out of your learning algorithms and make them work better for your applications. The fifth recommendation is to describe your input and output transformations with your model. So when I think about putting learning in an application, I think I have this problem, I can solve a lot of it, but then there's this big giant hole in the middle where I just have this question mark of there's some key problem I don't know how to just code up myself. And typically what I do to fill that box is by putting in some machine learning model based on some data. But most machine learning models, represent, you give them some representation in some vector space, some d-dimensional vector space, and then they have some output. Maybe it's just a single scalar, maybe it's some multi-class output that's again in some features or some vector space. But when I'm thinking then about plugging this into an application, the application might say something, well, I have like a user, and then I need a set of recommendations. And so this question is, well, how do I go from this user to features, and then go from the output back to the set of recommendations? And particularly the problem comes up, is this application code or model code? And the two levels here are really about doing feature encoding, which is a very common part, an important part of doing machine learning is figuring out what features to use and how to iterate on them. And then finally figuring out how to decode your output to actually build something useful from it. And what I say is that it's much easier to make this actually part of the machine learning model because they're vital for it to be successful. And then that makes for a very coherent interface for someone using a machine learning model because it means you can swap out lots of different implementations and still kind of operate in the same type of domain objects that anything that the application would expect. And so this is an example of how we would define such a thing in something like Netflix. So if we say we wanted to rank some videos for a given user, we'd have a simple API like, if you're given a user a list of videos, return a new list of videos. And then to give a model that we'd use in the system, we can just describe it by saying, hey, it's a ranking system, it's a ranking function, it's using these features, which can be parameterized, and then we use some definition, say a linear function that combines things together. And that by using a definition that encompasses how the input's being produced as well as the model, we can easily experiment and try out lots of things without having it so that we have to constantly kind of integrate application code with each of these different things. Sixth recommendation, don't just rely on your metrics for testing. So I think in machine learning, there's a temptation, which is that when you try out things and there's kind of a natural validation cycle, right? Which is that you have a test set or a validation set and you have a metric, and when you try out something and the metric goes up, then oh great, this is working. It's exactly what I wanted. This is what I'm trying to do. And it can lead to people to sometimes feel like, well, I'll just try things, and if it works, I'll know, and if it doesn't, well, then I'll move on to the next thing. But the problem is when something doesn't work, you don't know if it was because your idea was wrong, or was it the code you're using, or there was something bad in your data, or was it the metric itself had problems. And the reality of building machine learning software is that it's very intricate code you have to write. And it involves a lot of math and logic, and you can easily run into things like rounding issues, lots of corner cases, and something as simple as swapping a sign on your code can make the whole thing work or not. And sometimes your math you derive or the paper you're basing it on has it wrong. So the only solution that I kind of suggest here is that you have to unit test your core machine learning code very well to make sure that it actually works the way you expect, so that you can figure out, okay, was it my idea, or you can be confident that if something works or not, it was your idea and not just your implementation that was wrong. And I'll especially mention that testing your metric code is especially important, because if that's what you're going to be using to make your decisions about how your system works, that you want to be extra confident that that's actually doing what you think it's doing. And finally, though, unit testing things is enough. When you build these systems, it's easy for having your data pipelines not work properly. So you want to make sure you're actually able to look at how your whole system performs and provide larger scale tests on that as well. So to conclude, I think that machine learning is kind of and traditional software development are two ways of solving computational problems, and they have a lot of parallels. So with software development, you typically, if you have a problem, but hey, I know how to just code up some logical solution to this. You know what to do. You can write some code, you compile your code, you test it, and then you can deploy it into production. For machine learning, you may not, when you don't know what the solution is right away, but you have some relevant data, that's where you can use machine learning to solve the problem. And here, rather than write code, you develop one of these algorithmic approaches I was talking about at the beginning. Rather than compile your code, you're training your model based on the data. Rather than testing your code, you're running it through these validation metrics. And then finally, you also want to end up deploying in the system. And for machine learning, because it's kind of a higher level algorithm, each of these steps typically involves doing software development. But I think there's also a lot of opportunity in terms of a lot of the focus of the machine learning community is about how do you just, it's like having like what machine learning algorithm you should be using, and really that's like being obsessed with compilers when you're writing software engineering, and there's a lot of other parts that need to work for your system to work properly. So I think there's a lot more that can be done in that area. So takeaways for my recommendations to building machine learning software. So building machine learning is an iterative process, so making experimentation easy is important, like Ben was saying. Taking a holistic view of the application where you're putting learning. So you're not just doing learning to just figure out your one subcomponent, but think about once you put learning into an application, now have a whole learning system. So you want to be able to apply the same methodology you would just do for that subcomponent to the actual full system that you're now enabling learning. Design your algorithms to be modular so you can easily tune them for your application and get the most out of them. Look at the easy places to parallelize first, and use those before you get into the deep distributed computation. And that testing in machine learning can be very hard, but it's very worthwhile to make sure that things are working. That's it. Thanks everyone for your time. I don't think we have time for questions, but if you want to, please come grab me afterward.